Welcome to the Software People Stories. I'm Shiv.
I'm Chitra.
And I'm Gayatri.
We bring you interesting, untold stories of people
Associated with the creation
Or consumption of software-based solutions.
You'll hear stories of what worked,
and sometimes what didn't,
you will also hear very personal experiences.
and insights that would trigger your thoughts
And inspire you to do even greater things.
Hi Rinka, welcome to this episode of the Software People Stories. It has been a long time since we connected. For the benefit of our listeners also, we start with your own self-introduction. I guess you can do it much better than whatever I knew you were doing.
Hi, Shiv. Myself, I have about 35 odd years of experience in the software industry, and I've done all kinds of stuff, worked for large organizations, small startups. I've done, this is my second journey in startups. Apart from that, that was my day job. Night job has been other stuff also. So we created SPIN Bangalore together, and I think we did a nice job about that. That was pretty nice, and I enjoyed doing it, working with people, completely outside the regular job. So a bit of background on me. My basic background has been obviously in software. It's been primarily in the operating systems and the protocols, networking protocols in the embedded space. And I've worked in companies like Novell, Future Software, which is now Arison, places like that. And we did a startup in 2005, 2005, yeah. Came out of that and then went back again into the startup field in 2012. So so that's what I've been doing.
Yeah, wonderful. Yeah, I think first when I met you, it was during the initial BSPIN days.
Yes.
One question that has always kind of intrigued me is that when we talk about any process or structure, or when you mention protocols, people who have been working with operating systems or closer to the silicon are more used to.
Right.
But when it comes to application development in the large, for instance, how did you get interested in the concept of something like SPIN?
Okay, that was a very interesting journey. Actually, what happened was in my first job, that was in Delhi. It was a small company, IBM company. They decided to implement quality, and I was just this rookie software engineer, and it kind of made sense to me in the sense we do a lot of development, but it is all it's more of an art. You splatter the color and you don't know what you're going to get, and that was one of the core reasons why you don't know whether a project's going to succeed or what's going to happen, and you do want to get a little more control on it. So those days it was more like, okay, what works, what doesn't work, can we collect that and make things work better? Started from there. And yes, of course, being, how shall I say, under the hood, or away from the user's eye in the operating system space or the protocol space, it is very important to be structured and to be very, very clear how you're going to exchange information, how you're going to work, and what's going to work, what's not going to work. I think that all came together for me. And because see, one of the things is when you have a computer, and those days computers were not as stable as they've gotten today, you do want stability, right? And especially if you are a router or a switch somewhere out in the internet, you don't want to lose packets, and you want your connection to be stable. And it is only then you can run these long-lasting applications on top. The switch or the router has to disappear. And to do that, it has to be stable. And to do that, the quality has to be very high. I think that was one of the big triggers for me. And so quality had been a lifetime journey. Also, kind of related to that was in Future Software, I acted as a quality manager. And the one thing I realized, quality is really about collecting the best practices of an organization and making sure everybody uses those best practices. If you don't, then you'll have varying levels of quality, varying levels of trust. So you need to do that. And so the next step was obviously, can we collect those practices across organizations, which is what the quality systems were about. So there are two parts to it. One is, of course, having collected them, rolling them out, and the second is learning new practices and trying to roll those out, which is kind of part of what I've been trying to say to people, that we need to start, quote unquote, inventing new processes or discovering new processes. So, for example, Agile was discovered by some people, and so now it's become mainstream. But yeah, there was a time when people would look at Agile, oh, do we want to do this? What is this? So yeah, I think all those have been part of the journey that I've made, and which is where I thought Spin was a great way to, collect knowledge and also share out the knowledge. So that is how Spin happened for me.
That's very interesting. In fact, I'd like to pick on one thing that you mentioned in the context of routers. You said stable connections. I'm just transposing that to something that BSPIN was able to do, which is to establish stable connections across organizations, at least in the Bangalore ecosystem. Since you were initially probably doing a lot of evangelizing and then getting everyone to rally around the concept of sharing, benchmarking, learning together and all that. How was that experience?
Okay, that was brilliant actually. I remember the first time I really started on that whole benchmarking thing, Robert Camp's book on benchmarking. And my thought was about discovering new processes, or at least bringing processes from outside in. And I first talked about it within the Spin group, and the core group was like, okay, let's look at doing that. But now how do we do it? I'm not sure how to do it. And I remember then reaching out to a couple of seniors in the industry. I reached out to Sarla Ravishankar of Motorola. And she says, yeah, if you're doing it, I will get my quality guy to attend. And then I reached out to Philips. That was Nagarajan, SN. SN said, yes, we will get our people also into this. And of course, there was Shri, there was Indradepal, and there were a bunch of other guys who said yes. And I remember, I said, wow, I mean, people are saying they want to do this. Why would you want to share data? I mean, data is like my personal property for every organization kind of thing. But we actually managed to get people into a room, maybe 7-8 guys. And, everyone was like a cat on hot bricks, tentatively walking around each other. And so whole discussion started, okay, how do we share data? How do we protect each other and stuff like that? And I think the first 2-3 meetings went in the first, okay, we need to have a legal agreement. And so we wrote up something. They took it back to their legal, and then there's a whole this thing, legal giving inputs and it all getting rehashed. And I think that logjam was broken by Sri Shela. One day he came in, he says, okay, stop. And he put up the data of something like 40 projects up there. And that broke the logjam. And people started sharing. And I think the first decision was, take the easy part, which was, okay, can we benchmark across each other and figure out how Bangalore is doing? So then we started having numbers like, okay, we do 5 lock a day development and, things like that. So then that becomes a standard way of for project managers to predict what the project is going to be like. How many defects, how many locks per day, how long does it take to write specific documents, things like that. So I think that's how the benchmarking SIG started, really. It was, how shall I say, it was brilliant. It was totally brilliant experience.
Yeah, we always say that software is a team sport. So getting everyone together to a common objective, that too from different organizations having different ways of working, I think was definitely a major breakthrough in terms of how the community started forming and learning.
Right.
Now, extending that, have you been able to use any of these concepts that worked across companies within organizations that you were part of?
I think the biggest, and I would say the biggest global movement of this has been the open source community. If you look at what Linux has done, the whole the open source community itself. Basically, in the early days, what would happen is everyone would own chunks and components and stuff like that. And, everyone would develop and own their own IP. But then we got to the point where it made a lot of sense to start using open source components, if you will. And I remember in Novell, when we first started looking at the open source movement, it was a pretty jaundiced eye. I mean, if I integrate an open source component, then my I have to release my code, and that becomes a little dangerous. I think that movement actually took off. I think there was a recession, and people realized that, oh God, we can't, and we need to move to Linux, and we need to do it faster. And so one of the things, I was working on this LDAP project, side novel that was called eDirectory. One of the decisions was to port LDAP to Linux, and I was the lead on that. And when we started porting LDAP, now LDAP eDirectory on NetWare was one of the most scalable and most stable LDAPs in the world actually at that time. And so we decided to port it to Linux. And so the first question was, okay, there are so many other components that it integrates with. What do we do? How do we use it? And so we made a decision that we would use the Linux components as much as possible instead of using the components that we had developed inside Novell for NetWare. And with the result, the port was actually pretty fast. We released the whole LDAP release that goes on the NetWare CD that included a Linux component, and that was released in 6 months. Normally an effort like this would have taken us a couple of years, but because we use a lot of the open source components, we were able to do it much faster. And of course, a lot of our customers liked it, and they started using eDirectory on Linux almost from the day one. We found quite a few pilots and customers for that.
That's interesting, because one of the biggest challenges that most teams face, or when there are multiple teams within an organization, is what we call as this NIH, or the not invented here syndrome. So what tricks did you use, or how were you able to get a larger group to accept using code that was written by somebody else?
Let's be brutally honest about this. The NIH syndrome cannot be broken. It doesn't matter what you do, you can't break the NIH syndrome, because I am invested in my product, and if you dare touch my product, I will kill you. Okay. So the only way to break the NIH syndrome is if there is a pressure from outside, significant pressure from outside. In the case of eDirectory, what happened was there was a major recession, and Novell had to release a low-cost eDirectory on other platforms. And the only way it could have done that on Linux is by actually putting it there. And if they would have tried to rewrite all the components of the NetWare on Linux, it would have taken way too long, and they had to get it out very quickly in the market. So there was an external pressure. I'll give you a couple more examples. IBM, I had worked in IBM. So what had happened was, this was for, I won't name the company we were working for, but this was a very large telecom company in IBM, in US, one of the largest. I won't name it, of course. One of the things that IBM owned was it owned a defect tracking system that the company would use to log defects, track defects, and so on and so forth. Okay. And for this, the IBM had a team of 300 people maintaining that defect tracking system. The question was that why won't we use an open source defect tracking system where you do, you immediately eliminate 300 people and you cut costs accordingly. But neither the company was invested nor was IBM invested, because IBM obviously wasn't, because it was putting up 300 people, but the other company, no, this has been customized for our needs. But then again, there was extensive need to cut headcounts, and there was each line of code has a certain number of defects, so there was a need to cut defects. How do you cut defects? You cut it by, one very quick way is by integrating a stable component. So you take an open source stable defect tracking system, modify that, or at least file defects to modify that to suit your needs, and integrate that. Well, you've cut out 300 people. That's the other thing. I think I learned this in Novell when I was doing IPv6. IPv6 is the next generation IP that now goes on Novell NetWare. We wrote up IPv6, very stable, and we went to every product manager and we said that, hey, integrate it into your product. And Novell has many products. And they would all look at it, yeah, wonderful, great job. I think you guys have done a brilliant job, and it's as good as a TCP IP. I own both IPv6 and TCP IP there. So they said that, yeah, we'll do it. We'll put it on our roadmap, things like that, but nothing would move. I think it was 2003 when the US DOD, actually the US Navy, reached out to Novell and said, what is your IPv6 roadmap? Our next generation systems will all have IPv6. Suddenly, in one day, I had every product manager send me a mail asking for a call. Hey, can we start working on integrating IPv6 like yes? So you are not going to make any change if the pressure is from inside. Everybody's invested in the current system. It has to come from outside and break the system. So you have to figure out a way which breaks the system from outside, not from inside. It'll never work from inside. Incidentally, this is why companies get disrupted.
That's an interesting thought, creating disruption from outside.
It has to come from outside. It is only when you're dying that you're willing to take chemotherapy. It's painful. It's intensely painful. But the bigger pain is you'll die. Right?
Yeah. So 2 more questions around the open source theme that came up was that the culture, at least of acceptance of open source components, has definitely now grown, and then a lot of people are using it. To the extent some people say, I only want open source, I want something that is free.
Right.
How do we make sure that the open source movement thrives by making more people contribute something back?
So I think there are two, three threads here. Shiva, I don't remember if you remember the discussion you and I had, and this was like in 2001. I still remember that discussion, and it was around those days. Open source was not very stable, and you had asked, so why would one use open source? And I said, because it's cheaper, it's free. And said, why would you? So, I mean, essentially what it was that what makes it valuable is you can have multiple people come up with multiple similar components and you can pick and choose. And so what open source does is gives you an alternative to the closed source. And so the closed source now has to hustle and offer so much more value, which is becoming more and more difficult because people do migrate to open source. Now the trends that are happening in open source are really, if you look at some of the new companies, they do their go-to market as open source, and then they have a premium component. We're doing the same as part of our startup. So we are focused on analytics, and short and sweet, basically we are at the intersection of supercomputing and big data. And so what we are going to do, for example, is come up with an open source component that we put it out there and integrate with other open source products. So it adds value to the open source product. And so because what we are doing will make, so for example, we work with Lucene, which is a search engine. If we can make Lucene run much faster, then we expect, and this is the model that all the NewSQL databases have taken, we expect a lot of people to start using this accelerated version of Lucene. And so then they'll come back to us, hey, we've got this defect, fix it for us. And so we'll fix it for them as long as it helps everyone. But if they say, okay, we want a certain SLA, we say, okay, pay us for the SLA. And so that is one way of making money in open source, by getting maintenance contracts. And the other one is, we'd say that, okay, you have this accelerated version, but we use now 10 cards in parallel on a large machine, and we give you a version that is at least 20 times faster than the one that you're using currently. Do you want it? Because that 20 times faster means they're cutting out maybe another 10 machines that will do search, right? Without compromising on speed. They say, okay, we're saving so much, we don't mind giving you 50% of that. So then that becomes a roadmap to premium revenues. And this is why, if you look at IBM bought Red Hat. It was, I think, $16 billion. And that's the reason they bought Red Hat, because it allows quick penetration into markets where people can't afford much. But as people, get more and more used to it and they need more stability, then they're willing to pay for it. And that is where the money comes. If you see a lot of the formal, quote unquote, formal efforts that are going into open source, they are all driven by companies. Red Hat, IBM, Novell, apart from the other companies like Ubuntu, etc. So this allows for a huge amount of work going into open source. The second part is you have the chutku guys, the small guys, people like me, who want to make an entry. And if I try to go and sell, the first question I'll get asked is, okay, how do I know you're going to be there? Now, if I'm open source, I'll say, hey, the code is there, out there on GitHub. If I'm gone, the code is still there on GitHub. The second part is now GitHub has become the resume for developers. So if I want to go hire someone, first thing I'll ask him is, okay, give me your GitHub. Let me take a look at what code you put out there. So now people try to contribute to open source in order to, build a resume for themselves. And oh, by the way, if they find an interesting problem, that might actually translate into their doing a open source component or even an open source startup. So there's a lot of, how shall I say, churn or manthan that is happening underneath, that bubbles up into people contributing and small startups starting, as well as large companies contributing, and the whole ecosystem enriches around it. And this is something that the closed source companies are finding more and more difficult to challenge, because you do something, there will always be some guy in the open source who will go and do something similar, right? And then what do?
Yeah.
Your the value you bring keeps reducing as a comparison to the other guy.
Okay, now this actually also leads me to the second question that I had, which is also one of the topics that you're passionate about. We've talked about it also in the past, about new ways of software development, right? Now, in the context of open source, there is a common protocol. There are multiple contributors. When you want somebody to review, it's not only about what you write, it is also about how you write. Whether the code is stable, whether it is secure, whether it is high performant, efficient, and all that. Now, when a change needs to happen or change happens in terms of how software is developed, would that make it difficult for the open source movement? Because unless every contributor understands the new protocol or the new ways of development, would it still be as effective?
Actually, yes. And it is not the contributor needs to understand it completely. The whole thing is driven around the review of the code submitted or the patch submitted. See, what happens is the whole thing is driven around the review process. If you try to implement this kind of a review process in a closed source system, it will become horrendously expensive and very slow. But in an open source, the cost is zero. So there is no cost, and that is why. So let's say I submit, let's say I'm not a newbie contributor. I've submitted a few patches and so on and so forth. I've taken the defect, I fixed it, and I submit a patch. Now, the act of submitting a patch has got 2-3 things. The first is actually taking the defect, telling everyone, hey, I'm taking this defect. The second part is saying, okay, this is how I plan to fix a defect. Now you have multiple people commenting on how I plan to fix the defect, and look at it as points of view. So one guy will bring the software point of view. Second guy will bring a reusability point of view. The third guy will look at it and say, hey, from a cybersecurity perspective, you need to consider the following things. The fourth guy will say, okay, from a performance perspective, you need to look at the following things. The fifth guy will say, okay, reliability, the following things. Now, if you see, these are all points of view that have been contributed, right? Obviously, it will take time to contribute this. So it is not something that I will get inputs in a day or two. It might take a couple of days, maybe a week to collect these inputs. So first of all, what happens here is, as I get these points of view, I'm enriched. I'm significantly enriched. I'm far more enriched than I would be in a closed source company, right?
Okay.
Because first of all, there may not exist such people in a closed source company. I mean, people won't have the organization will not have the money to fund such people, first of all.
Right.
Secondly, even if they did, look at the amount of time needed to do this. Okay, so now I make the fix, I test it, and I release the patch. There's every application or component has got its own way of releasing the patch, and they usually publish the process. Now, as they release the patch, all these people with various points of views, they look at it and they comment on the patch. And then the guy goes back, fixes all those comments, and then releases it again. And only then, after everyone has accepted it, gets rolled in. Now, if you see what is happening, the whole release process here is much, much slower than what would happen in a closed source company, but the quality is much higher.
Okay.
Right? And with the net result, over time, the quality of the open source component actually keeps on growing. And one more thing that can happen and does happen in the open source component is what is known as the refactoring overhead. At some point, when the code gets too unwieldy, somebody decides, okay, this is looking really awful. We need to clean this out. And he says, okay, I'm going to refactor the code. And so then they go and refactor the code and submit it.
Okay.
Imagine doing a refactoring of a large application in a company, software company. They will say, hey, boss, refactoring, it's expensive, zero value, and no company is going to pay us for it. It is simply a cost for us. Let's not do it, right? So the code keeps deteriorating with time. That is not the case in open source. It keeps renewing.
Okay.
Right? And by the way, this whole process is a mechanism of accepting the quote unquote right, not accepting is the wrong word, getting the right kind of people in, because you need to have the patience to go through this. And the people who come in become much better programmers, architects than you would have in a closed source company. In fact, I think some of the best global architects I've met are all open source contributors.
Wow.
Yeah, interesting, isn't it?
Yeah, I'll come back to this as we close. I have a favorite question, but before that, since you also mentioned that you work in the intersection of open source and large volumes of data, how do you think the open data movement is progressing?
So I will approach this question from two perspectives, and that is also related to your question about the software trends in the software industry. So there are a couple of things that are happening today. Let me enumerate these trends. First, we know that the Moore's law has come to a halt.
Okay.
And the reason it has come to a halt is a couple of things. Number one, you can't shrink silicon very much further, right? I mean, we've kind of reached limits there. That is one part. The second part is you can't clock it faster. Now, as you clock silicon faster, clock CPUs faster, more heat is generated. And with finer silicon, there's a good chance that you will actually burn your silicon. So you can't really clock it faster. Okay. There are answers in the sense you can use nitrogen cooling, and academic tests have shown you can go up to 7 gigahertz with nitrogen cooling, but you can't really do nitrogen cooling in a data center. So I think the limits there is kind of like 3 gigahertz kind of thing, and still the heat generated is massive. So that is one part. Now, if you look at any computing environment from an infrastructure and a big data perspective, I will take 2-3 perspectives. One is from an infrastructure, and the second is from a big data and the open data perspective. I won't go to the open data so much as I will go to the big data, because big data is both open and closed data. So one is this problem with silicon. The second problem that we are having is we know that data or rather networks are scaling, but they're not scaling fast enough. They're kind of scaling. So Ethernet, we know, will continue into the future and will continue to scale, but there is a limit to how much Ethernet will scale. And so the network fabric will also become a limitation in the future. And the third problem is, of course, the storage, getting the data out of the disk or the NVRAM or whatever into the CPU to crunch it and put it back.
Okay.
Now, this is from the infrastructure perspective. Now, if I take an orthogonal perspective to this, if I look at big data, now, there was this very interesting study that year on year EMC has sponsored with IDC EMC. You can Google that actually. That talks about data growing from, it grows around, I think 10 or 12 terabytes in 2010 to around 44 exabytes in 2020. It is an exponential growth actually. So the problem here is a couple actually. Now that you are having an exponential growth of data, the only way to handle this is if you take a chunk of network storage and compute, a chunk can handle just so much data at a time. Now, if you're having exponential growth of data, the only way you can do it is by increasing the sizes of your clusters. About 2 years ago, I talked to somebody in Oracle, and they were talking of 100,000 machine clusters becoming common, pretty common. And that was 2 years ago. And with exponential growth, I would expect that to double.
Okay.
And that is a limit. So one of the biggest issues that data centers have today is evacuation of heat, which is why one of the things that a lot of data centers are doing is they're moving to places like Iceland, or they're burying it underwater. So that heat evacuation becomes not such a huge problem, right? Because you need huge amount of power to, first of all, air condition it and then evacuate the heat. Data centers have started consuming power in megawatts, and it's now going into multiple megawatts of power. And as we move into the exascale computing, one of the reasons that exascale is such a huge problem is that setting up such a supercomputer or a data center, if you will, these are now span multiple acres, and I'm talking of Google kind of data center. Why is this important? As data grows, we will need such data centers to handle the data, right? And they're going to become pretty important, critical. In fact, now data centers, the power consumption is now something like 2 to 3% of the global power output. Is like, and it's growing, okay? It's growing significantly. So what do you do? See, okay, so that is one perspective, one facet of the problem. The second facet of the problem is if you look at computing from the dawn of computing has been sequential. And that has been primarily because in the early days, most of the applications, especially in the commercial space, were MIS kind of applications. So, HR, whatever, billing, etc., was sequential. Now, what would happen is, what does that mean is you take a piece of data, load it into the register, process it, remove it, put the next one and process it. This is fine when the data sizes are not very large. But as the data sizes explode, the time to process is a function of how fast you can load it, process it, and return it. Which means that time to process also keeps on increasing exponentially. And so the only answer to that is to throw multiple machines at it and chunk the data. And this is a crude form of parallelism, if you will. And this is where the Hadoop and the Storms and Apache mouthful, if you will, have come in. Now, what is happening, if you look at data that is being generated, we categorize this data into three types actually. The first is the traditional sequential data, which is more like, which is actually, if you see, is a business process is a very good example. It flows through various applications and is handled individually, and so it's sequential. It has to follow that sequence. Otherwise, the business process is broken. The second form of data is something that is orthogonal to these applications. It comes out of the log file of these applications, it comes out of sensors, and these are all parallel data in the sense the data are not related to each other, except maybe in terms of time or temporally. And you can actually process them together, I mean, in parallel. So if you look at it from this perspective, I can take chunks of this data, and if I process them in parallel on different machines and then pull the answers together, then I would be able to process them much faster. What we do is we use parallel elements on a single machine. So these are what are called general purpose GPUs. These are used extensively in the supercomputing environments. So what happens is, like I talked before, that now you can have one chunk of compute network and storage, do a certain amount of processing. But if you can do parallel processing inside that, the compute logjam is broken. And if you can pull it all together in as on one machine, then the disk acts as your storage. And so all you have to do is to move stuff from the disk into the GPU, process it there, and return the results. So which means the level of compute that you're doing is much, much faster. Now, the other side, this, I talked about this IDC EMC curve, right? Today, I think around 10 to 15% of the data that is created is the sequential data. The rest of it is parallel data. And we're using sequential machines to actually process this parallel data. Right? So if we use parallel machines to process this parallel data, then amount of machines needed, the amount of compute, storage, etc., storage would not go down, but the compute and network would definitely crash. So to give you an example, my competition, they are doing parallel databases, and they claim something like 2000 times speed up over a sequential database, such as MySQL or Oracle and so on and so forth. So as a tech demonstrator, I wrote a proto database, if you will, that would read data and run a SQL query on it. Now, I took an open source database available on the net, some 28 million records, loaded that on MySQL, and I loaded the same data on my proto database and I ran a query on it. My proto database, which used a very old parallel GPU, very, very old, it's obsolete, completely obsolete. It has around 192 CPUs, ran about 100 times faster than the MySQL database. Okay, the new GPUs, the high-end GPUs, which by the way don't cost very much, the high-end GPUs are like 2 or 3 lakhs, would have allowed me to run this at least 3,000 to 4,000 times faster than MySQL.
Wow!
Right. So the thing is, we need to look at the whole paradigm of how we do software development and how we do compute, we need to start thinking parallel. And this is a major issue, because if you look at how we are educated, how we are taught, right from the first Hello World program we wrote, everything is sequential. I mean, Shiv, how many people do you know have written multi-threaded applications in the application space? I bet not one is multi-threaded. Or if they are, they will be just 2 or 3 in your entire experience.
Yeah, actually, probably interesting trivia is when I started my career as part of the initial induction training, we were asked to write something like this, where you spawn off processes. I mean, everything will come, and then there is one mother process that will generate a token. And then the children are supposed to be waiting for that. And then as soon as they got one, they'll say, I ate a cookie, or I got a cookie, something like that.
Right.
And then that also turned out to be a little bit of a challenge for me, in the sense on one of the first assignments, there was something that had to be done about optimizing the printer.
Right.
Where multiple applications were printing. And I said, okay, let me just use this.
Right.
This concept. But then the first time the program ran, it crashed the system.
Yeah, so you have to worry about race conditions, writing each other's this thing.
Right, because what worked in a small maybe test or a learning application, and then when you put it in production, running on 2 different machines, everything racing for a common resource. Okay, then I slowly learned how one has to coordinate this and so on. But yes, it's definitely interesting, and it can make things much simpler, but a little challenging.
Look at it this way. Now, you wrote this program for a CPU that had maybe 2 cores. So you would be able to run maybe 2 threads, or with hyper-threaded, maybe 4 threads in parallel, right? What if you had a CPU that had 7,000 cores?
I can't imagine that.
Yeah, so that is where compute needs to go. And so we know a couple of things. We know that the mainstream programmer can't do this, will not be able to do this. He's not educated. So what we're doing is, we believe that we need to come up with key components that actually parallelize. The programmer just integrates those components of libraries, and then offloads his work to that. It is slow work. It is very slow work. And debugging something like this, as you discovered, is very painful. On a CPU, what would take like 15 minutes to fix a bug takes about 2 weeks on this. But if we don't do this, pretty soon we'll get to the point we will have what I call dark data. Data we can't process simply because we don't have the compute capability. I mean, you throw 200,000 machines at it, 300,000 machines at it, and then what? And you still have more data you can't compute. What do you do? The only way out is to throw it away or not collect the data, which is also not acceptable.
Yeah. So would it be fair to summarize that big data has opened up big challenges to explore, research, and fix?
I think the challenges are just coming. You're right. The challenges are just coming. And the answers, the answers are temporary also. Because I think the core of the problem here is, I believe, the whole von Neumann's model, which is like a basic axiom on which all of computing is based, is broken actually. I know that's like throwing a pretty large bomb into the thing, but I think we need to look at a completely different model. And no, that model is not neural networks and things like that. But we need to look at a completely different model of computing. Even parallel computing, as I'm talking about what the components do, each of the CPU is a von Neumann CPU. So there is sequential computing there also. They are, and the problem is we don't have, all that stuff about quantum computing and all that. That's way in the future. People are putting out stuff out there, but there's nobody I know who will deploy a quantum machine in his commercial network. First of all, no machine is there. Secondly, there's no software. Third is, how do you write code to it? How do you develop on it? There's a whole bunch of stuff that's not clear. So the problems have just begun really for us.
Yeah, I think this would merit another conversation, because today we are almost running close to the usual length that we maintain for an episode. Okay. But before we close, there is one favorite question that I always ask most of my guests is, what would be your advice to someone who's considering getting into IT or software, or somebody who has just entered, particularly in the context of, say, open source that we spoke about, and people using that to enhance their credibility or their resumes by posting on GitHub and all that, what could be some things that somebody should know or should be ready for and actually do something about it?
Right. So I'm going to be controversial. I always am.
Please.
First of all, don't go and join Infosys or a Wipro. Don't. You will be limited. What you should do is identify, if you really want to get into software, understand a couple of things. The days of the generalist are over. You become a generalist, you'll find a job, you'll grow for around 5, 6 years, 10 years, and then you'll be redundant and you'll have nowhere to go, because your only route out will be to become a manager. And we have way too many managers. We don't have enough specialists. So your choice is really to become a specialist. Become a specialist. And the best way to become a specialist, find out what you like. When I was a kid, I knew that I wanted to get into protocols and embedded systems. And so everything I did was towards that. And I worked about 10 odd years in the protocol space, various kinds of protocols, embedded systems, and the RTOS, real-time operating systems kind of work. So as you become a specialist, you become more and more valuable. You will not have a fast growth, fair, but at least you will have a growth and you'll have a roadmap. And more importantly, you can contribute to this system. And the best way to contribute to this system is identify an application that you like more than the logical like. It has got to be emotional attachment to it, and go and start contributing to that open source system. Just keep contributing to it, learning from them, and growing from there. Over time, you will understand the problems and you'll be able to do your own component. This is really who you are in the software world. And this is what the good guys, the seriously good guys, the Googles, the Facebook look for when they go hiring. Once you do that, see, it doesn't have to be that you have to get hired by a Google or Facebook. You might just find a component that you can then spin off and do a startup around, in which case you don't have to worry about a Google, because you might end up being acquired by them. So I think this is a route a lot of the software engineers will have to take. And also, it is this that will slowly build your capabilities of understanding how this system fits into other systems and grow into being an architect. See, the one thing we are desperately short of in this world, in the software world, is having good, or rather great, global level architects. We have very few, very, very few. And sadly, all of them are in the US. None of them are in India, or very few are in India. What happens in India is everyone becomes a manager and they destroy their capability of being able to design. Finally, I will leave you with one thought, what Bill Gates said. Don't beware of the nerd, for he might be your boss one day.
Yes, boss. Knowing you as a nerd.
But not that bad, I hope.
It's good, Rinka. I think there are a few more questions that are there, which will definitely be, or making the next conversation more like a debate, particularly one that you are talking about in terms of becoming specialist and maybe super specialist versus everybody wants to be, or everybody wants a full stack engineer nowadays.
Right.
And of course, a few things. So thanks a lot, Rinka. It has been wonderful and a lot of new ideas to explore further. And as usual, you have your own point of view, which has been radical at times, but then they've always created the effect or been able to create an impact.
Yeah, thanks a ton. It was a pleasure talking to you, Shiv, as always. I always enjoy talking to you. So it was good. Thank you.
Thank you, Siddharth, for composing the intro and outro music for this podcast.
If you like this episode,
please subscribe on your favorite podcast client
and spread the word in your network.
If you'd like to share your story,
contact us at podcasts@pm-powerconsulting.com.